All right, welcome to the chapter of Chapter 10, where we're talking about bulk electrolysis and related methods to bulk electrolysis. As we were finishing last time, we were talking about using controlled current methods and also using those same ideas in controlled current methods but as in controlled potential methods for doing bulk electrolysis. Before we get into the notes that I've handed out, let me just mention a few things about bulk electrolysis for electrosynthesis. We'll have a little bit of time at the end of this particular course to talk about electrosynthetic things that are happening in the world of industry. But let's just talk about, let's suppose we're doing a reaction in which we want to use electrosynthetic methods to cause some sort of chemical change. As you know, you can use electricity as a reagent. You can oxidize or reduce some molecule to make some sort of desired reaction. And many chemical reactions that are done in industrial processes are oxidation reduction reactions. For example, combustion, a very popular method, is essentially an oxidation reaction, although you don't often think of it that way. We can use electricity directly, and in fact it is used directly in many cases. Often, though, it's not the cheapest reagent. We can mine natural resources that have stored energy that are cheaper than electricity. For example, coal is a reasonable reducing agent, and it's used as part of a chain of chemical reactions to reduce iron oxide to form iron metal. So we could use electricity directly to reduce the iron oxide in an electrochemical cell, but it's cheaper to use coal. One situation where it's not cheaper to use natural resources to do the reducing is the production of aluminum. There's no sufficiently inexpensive reducing agent that has enough power to reduce aluminum oxide or aluminum ores, aluminum containing minerals, to the aluminum metal. So they use aluminum. In aluminum they use electricity, and that's a significant fraction of what people are using electricity for in the United States, is the production of aluminum. For electrosynthesis, though, we might use electrosynthetic methods for smaller scale processes where we might want to use the cleanness of the reaction as an advantage. Let's just consider a simple problem. Suppose we had 1 mole of material that we wanted to reduce to some other process. So suppose we have a mole of ox plus it takes 1 electron to red. Well, if we do that 1 mole of material, we want to do that as rapidly as possible. We don't want to spend a year doing this electrosynthesis. We want to do it in a few minutes, perhaps, or less. Let's consider how feasible such a process might be. Well, in order to reduce completely 1 mole of ox to 1 mole of red, we have to pass 1 mole of electrons to do that process. Now, 1 mole of electrons is the charge on an electron times a mole, and that's going to be about let's see, that's going to be 100, let's suppose, I'm just going to round about 100,000 coulombs of electricity. Not exactly, but close enough. And let's suppose we need 100,000 coulombs of electricity. If we try to do this electrosynthetic reaction, let's say we want to do it really fast. Suppose we want to do it in 1 second. Well, let's think about how reasonable that might be. If we take 100 coulombs of electricity and put it through 1 second, into 1 second of a reaction, that means that we're going to have to pass 100,000 amps. So if we divide that by 1 second, we have 100,000 amps of electricity. Now, that's not something you're going to be finding lying around in the lab as a power supply, so we're not going to be able to do that sort of process. Perhaps industrially we could do it if we had a sufficient enough reason. Well, let's consider the other problem. If we had to pass 100,000 amps of current through our cell, we have to worry about the resistance of our cell setup. And even at 100,000 amps, we have to worry about the resistance of the wires that are connecting the cells together and things like that, not just the cell resistance. Even if we had a very low resistance, say 0.001 ohms, which is really difficult to achieve in practice, we still are talking about 1,000, I think so, 1,000, yeah, 100 volts of IR drop. In other words, we'd have to apply 100 volts of electricity just to drive the reaction to avoid the IR drop. At the same time, we're going to be dissipating quite a lot of resistance, and the amount of power dissipated in that circuit in one second would be 100,000. Power is equal to I squared R. So 100,000 squared, 10 to the 5th, or 10 to the 10th, times 0.0001, so 10 to the 7 watts. In other words, we're going to be needing 10 megawatts of power to drive that reaction. So that's obviously a situation in which we're not going to be doing this sort of reaction. Now, how can we minimize some of these problems? One way to do it is to make sure that the current density of our electrochemical cell is low. The other problem is, I guess I didn't mention, is that we also have a limitation, not only electrical, but we have a kinetic limitation. If we try to run this reaction so rapidly, it may not be possible, because the reaction will not, in fact, allow the reaction to proceed at that rate by electron transfer kinetics. So what will happen is if we try to force that much current through, the reaction will proceed by other pathways, and so we'll have side reactions. So a large fraction of the system may undergo side reactions. So what you want to do is run your reaction at a low current density to avoid kinetic limitations. Now, typical current density, even for a very rapid reaction, would be something like 1 milliamp per square centimeter. So if we want to run our reaction at 1 milliamp per square centimeter, which is a reasonable amount, of course that means that we're going to need to have an electrode that has 100 million square centimeter area. It's not necessarily that difficult. We could make a very large electrode, say with a carbon mat or something like that, and to do that reaction. So that's how we would get away with doing a very rapid reaction, by making a very large electrode and doing the reaction with a small amount of volume. Of course, remember also the problem is that we'd have to supply all that material to that electrode in 1 second. So we'd have to have some sort of a convective process or some way to force that material at a very high rate to the electrode surface. And so that's another particular problem. A much more reasonable process would be to extend that out. We might have to take 10 hours or so to do that reaction. Even then, we're going to run into some problems with IR drop and so on if you start playing with the numbers. So you can see that doing the reaction with electrosynthesis it requires a lot of additional considerations that you didn't have to worry about before. Size of the electrode, how much volume you've got, the kinetic limitations of the process, heating of the solution, IR drop, all these things we really didn't have to worry about in analytical electrochemistry that come about when we talk about using bulk electrolysis. How can we help ourselves? One is we're going to try to maximize area to volume ratios. We want to make the electrode area as large as practically possible while making the volume as small as practically possible, because that will give us the greatest advantage in mass transport to the electrode surface, and also will give us the greatest advantage in minimizing the effect of kinetic processes. Also, with small volumes, that means that the distance between the working and reference auxiliary electrodes is going to be small, hopefully minimizing the effect of IR drop. Of course, course, the problem is our electrode may be of an expensive sort. It may be we need a platinum electrode, so it may not be possible to have a really large platinum electrode because it costs so much money. So there's always practical things that we have to worry about when we're doing with bulk electrolysis. And of course, this is just a brief qualitative idea. There's many, many books have been written on industrial bulk electrolysis processes and so on. Just to mention, for example, in aluminum electrosynthesis, part of the interesting thing about it is that they're running their cells at not 100,000 amps, but tens of kiloamps per cell. But they're running at an overpotential of 3 to 4 volts, which means that the resistance is quite small. Their electrodes are very big, and so they have some effect. But the overpotential of 4 volts is dropped as a resistive heating, which actually helps them out. They need to heat the cell anyway to get the reaction up to about 900 degrees C. And so some of the heat that goes into the cell is used for that process. And so they actually don't have to heat it with some other material. Of course, resistive heating is an expensive way to go about it. We all know that it's cheaper to use gas heat, and because we can use the energy stored in the gas, chemical energy stored in the gas, cheaper than we can use the electrical energy directly. But that does minimize some of the losses we have with aluminum production. It's also one of the reasons that aluminum recycling is so much advantageous. We don't have to put in so much heat to do the aluminum recycling as we do to make the original aluminum in the first place. All right, well, the other things that we're talking about. So in this class, we're really not talking about bulk electrolysis on industrial scales, and we're just going to scratch the surface of bulk electrolysis for electrosynthetic methods. Perhaps we want to make something chemically. The other things we're going to be using for analysis, though, with a bulk electrolysis process would be things that are electrogravimetric. And it uses electricity to deposit some material on an electrode cell. And in fact, this is a very accurate way of doing it. We can measure current quite accurately, and knowing because of Faraday's relationships with Faraday's law that the electricity and amount of material deposit or amount of reaction occurring is very is quantitative. That means that by weighing the amount of material that we deposit, we get a very accurate determination of the charge to material relationships. And that was one of the original ways that they determined this Faraday constant, and still is, in fact, 96,485 coulombs per equivalent. They deposited by using very carefully amounts of electricity, quantitated amounts of electricity, silver metal onto an electrode, and drawing and weighing that very carefully, they deposited the relationship that we now call the Faraday. And it's one of the most accurately known physical constants by using these electrochemical methods. But people also did things before too with using electrogravimetry. They deposited metals and they weigh them. It's not a particularly accurate method for most things because most materials don't deposit a nice smooth film, so they get trapped solution, it's porous, things flake off when you're trying to dry it, so it's not as accurate as you'd like. Another much more accurate way of doing this is called coulometric, where instead of doing material to be deposited, you actually just do some reaction in solution to generate an oxidizing or reducing agent, or you can sometimes do things to generate, say, acids or bases in solution. And what you do is you essentially do titrations by electricity. You coulometrically generate some titrant. So rather than by adding it with a burette, you can do it with an electrode. And because you can measure the charge very accurately and even very small amounts of charge, it's very easy to do very exact titrations using coulometric methods. And that's a big advantage. Basically, you just find total charges. And so you need to have very accurate ways of determining current or generating currents and then determining the charge. The other major use of bulk electrolysis is electroseparations. where we're trying to remove components from solution. So you can use this. In fact, it's used quite a lot for what they call a, I forget the name now. They use it to strip out impurities in solution. For example, if you have a small amount of metal ions or something in solution, you can use a pre-electrolysis step where you electrolyze your solution for a long period of time to strip out the metal impurities, and it's often used for very careful experiments to try to remove the impurities that way. Or you can send it through your solution flowing through a plug of porous electrode material and strip out the materials as sort of a pre-step. In bulk electrolysis, as I said, the advantage is to use small volumes, large area. And so one of the things that people often use are thin layer cells. You use a nice small volume in a very thin layer. Of course, when you have a small amount of material, you don't have very many moles of material to analyze, so the reaction can occur quite quickly, and within a few seconds often you can completely electrolyze that solution and get the amount of charge, and from that you can get, for example, the number of electrons if you need to know that, or you can get, if you know the number of electrons, you can get the concentration and so on. The other thing that we can do is a stripping analysis that people use for analysis is that you pre-concentrate in a thin layer of material. And usually that thin layer of material is a mercury cathode. You electrolyze a metal into the mercury. Because the mercury itself is a much smaller volume than the original volume that you've got effectively a large pre-concentration step where you've concentrated your material from a large volume to a very small volume. Now when you do after you do the pre-concentrate, you can electrolyze from the thin layer. And if you remember all those things we talked about in electrochemistry, we always just talking about the concentration. The current is proportional to the concentration. For thin layer or adsorbed species, or for bulk species, it's proportional to the concentration. So by pre-concentrating, you effectively make the concentration in the very thin layer very large, and then when you do the electrolysis, the signal then is much, much higher. And so that's one advantage that you have with this particular thing. Now, the thin layer material often is mercury, but you can actually, for example, deposit metals on a, say, carbon electrode, strip them off. You can do it sometimes to do ions. You can, instead of reductively depositing metals, you can oxidatively deposit chloride ions by forming, say, a mercury chloride species, which then you can reduce off, and so you can determine ions in that particular way. So there's a whole raft of analysis that are involved with stripping analysis. We'll talk about that a little bit more